Good morning, everyone. It gives me immense pleasure to welcome you all to today's skill development program organized with the aim of enhancing students' technical knowledge and bridging the gap between academics and industry relevant skills. We are truly honored to have with us an eminent academician and researcher, Dr. M. Ashwita Garu, who is currently serving as the head of the department and associate professor of information technology at Cmrec Engineering College. With over 30 years of rich teaching experience, she has developed strong expertise in machine learning, data mining, and big data analytics, and continues to be an active contributor to research and academia. On the behalf of management, faculty, and students, I extend a warm and heartfelt welcome to Dr. M. Ashwita Garu. We are extremely grateful to you, ma'am, for sparing your valuable time and sharing your knowledge with us. Now, I request you all to be attentive and make the best use of this wonderful learning opportunity. Now, I humbly invite Dr. M. Ashwita ma'am to take over the session and enlighten us with her expertise.
Welcome back to a new session of ensemble method. Now, before people start joining here and not to waste much of time, let us take a scenario. To start off the topic ensemble methods, bagging or boosting, let us take up a simple scenario where go back where you have decided to join a particular college in engineering. Yes? How did you decide? How did you decide? By ranking? No, usually. How did you decide?
Seeing previous placements.
Okay. Did you ask some people? How many people? 10. How many of you suggested your college? The maximum? Yes? Okay. Another scenario. Okay, we go for a movie to watch a movie. How do you, if there are no reviews?
By seeing it.
Okay, familiar person. That is not the case I'm discussing. You ask people. Usually you ask the people who watched it, and majority of them say one time watch.
Yes.
So you say, okay, at least I can watch once. Or they'll say it's a super hit. Who say it is a flop? Will you consider? 8 say it is a hit. Yes? Yes or no? So you start going to watch a movie. That is one case where machine learning uses concept bagging. Okay? So in bagging, what the system does is, it asks various machines to perform, to decide, and based on the majority voting, it gives you the final results. Okay? Let us take another scenario where you have to conduct a freshers party, you have to coordinate for the freshers party. Okay? Well, yes, I can find you also disturbed. Very interesting topic, not to be missed. Okay. Now this scenario where you are going to organize or you are going to coordinate for a freshers party. And I ask people, how are you planning a freshers party for your juniors? There will not be a particular perception, one person who can give you the complete answer. Yes or no? One's perception will be on the culturals. One's perception will be on the food. And we might miss the finances. One's perception will be on the finances. And he might miss about the refreshments. One's perception will be on the time. Yes or no? So there is something that particular person misses out or cannot exactly coordinate with. Now, that will be taken as the input to your next module. So, discuss more on the finances. You will give something which you are missing, and that person will give another scenario where he is missing on time, and that will be fed into another module. So, here each one of you are a module. Okay. So, what you are planning will go as you give it to a base learner first. Base Based on the failures of that particular answer, you are going to feed that as an input to another model, and that next model is going to decide the next output. Likewise, you are going to take, again, you have the concept of averaging and voting, and then you are going to decide the final answer. So these are the concepts now what you are using in general life to get the best out of your particular scenario. Even machine learning also use the concept of ensemble methods. Okay, so now this ensemble methods is combining various techniques to get the best output. Now here you in the companies or in the real-time scenario, healthcare, you say you take banking, name it, and you have it. You have ensemble methods being applied or being used in a present scenario. Okay, to move on to the introduction, the ensemble is a method where we use many small models instead of just one. So you are not using one single model here, you are using multiple models. For the same training, you have the data set, training and testing, right? So training data set is going to be applied to multiple models instead of one model. Now let that be any model. Here in the examples we are using this series. Now so far you have been learning about various classifiers, predictors, various algorithms, right? Now these algorithms are used in combination, used several times, a single algorithm multiple times for the best results. Okay, so each of these models may not be very strong on its own, but when they are put in their results, you get a when they are put multiple times, when they are repeated, you are making a robust system where you are getting the best answer out of it. Okay, it will be shared, please concentrate. Right? Then it is like, same as I told you, you are asking a group of people for advice instead of one person. One person is not going to give you a complete answer. Every person has its own style. Now every person is a model here. So every model has its own style. It will be over-fitted, it will be under-fitted, or it does not accept the data for the various other reasons. So you are taking multiple advices instead of single advices and making the concept of voting here. Whoever is giving you similar answer, majority of the answer is the final answer. Okay? Like you ask in what you call a buffet, right? You go for eating food in a buffet, you ask people. So if majority of people say this food is good, that is good. By default, it is good. Leave it, how it works. Are you understanding? So this concept is going to work under that condition. Okay? So this is how it goes. Training data, this is your training data, and this training data is first divided into samples. Now how is the sample decided? Sample is, see, this is your model. Okay, this is model 1, this is model 2, this is model 3. Each model is given a different sample, but it is a bootstrap sample. Now how is it bootstrap? Bootstrap means there can be repetitions in the samples or within the same sample. Repetitions of the data items. Now see here, for example, this is a data item, this is repeated here. It is there here, it is there here also. It can be appearing in any number of training samples, and it can be repeated with the same training sample also. So now this is called bootstrap sample. This is called a bootstrap sample, and each sample, now when this is n and this is the size n and this is data d, you cannot expect the entire data to be given for a single learner, right? You should divide it into a d dash. If it is n, this will be size of m, or you can say m dash, whatever. Okay, so it is a part of your original data set. So in your data set, you are dividing it into a random bootstrap sample, and then you are giving it to the learner. Learner is any model. Like you can take a decision tree. Okay, decision tree you have been using, right? So the decision tree, you have this any decision tree, any depth, right? And that is going to give you an answer. Likewise, all the learners are going to give you the answers. The major this is then given for aggregation. Okay, so that is why even your bagging is called bootstrap aggregation model. It is called called bootstrap aggregation. In bootstrap aggregation, it is here dividing the sample into bootstrap. There is a least also. Okay. Why it is bootstrap aggregation means here the sample is divided into bootstrap samples first and then it is aggregated. That is why it is called bootstrap aggregation technique. Right? So basically this ensemble concept works in this scenario. Both your boosting and bagging. And another thing you have called stacking. Let us see the ensemble methods. Here, see, usually the ensemble methods are bagging, boosting and stacking. Bagging is where you are using multiple learners, right? Boosting is you use a model and its missed points or the errors or misclassifications are given as an input. Here also you use multiple models. Now here in stack, your entire data science, machine learning, you get this psychic module, right? Here you take an sklearn or ensemble methods will give you all examples. Like the example for bagging is random forest. So psychic learn from that module you can import the class. Okay, so these are the three techniques here. Next, this was discussed. Now, usually in ensemble learning, this was also discussed. So you have your training sample divided into bootstrap samples given to each classifier. Based on the classifier, it is given to the ensemble classifier where voting happens and you get the final result. Now you can use a test data to the ensemble classifier also. That is usually happening in bagging. Okay, next, the bagging algorithm. Let us explain. I will discuss with this the diagram. Okay. Okay, so now here in bagging, what happens is, first time you are bagging, you have to take the data set, bootstrap it. Here, what you are going to use is, usually in bagging, you use a model. We have shown this in ensemble methods, right? Same like this. After this, what happens is, this will release an output 1, this will release an output 1, suppose, or yes, 1 says no, and majority is yes. So you have two things here, for classification and for regression. So classification, what happens is, you take the voting, maximum number will be given for classification output. For aggregation, what happens, for regression, what happens is, you are going to aggregate it. That means, you have to average it and then you have to give the answer. It is like that. Okay. So first what happens in bagging, again the same concept. Here you have bootstrap sampling, then the base model training. Here you are not concerned about first output. Okay. Here all the inputs are treated same with the same weights. Okay. And all the classifiers are important. Every classifier is treated as an individual. Right? There is no like dependent classifiers here. So you model the base trainer here, and then you are going to for prediction you are going to aggregate, and then out of value evaluation is you are going to use it for testing the performance. Okay, so you are going to use this out of value evaluation as testing on the performance check చేసుకోవడానికి same classifier you are going to use it again. So it is not going to make much difference. Okay, even though it sounds similar, right? Sounds similar, but there is still difference with it in a while with the examples of the application algorithms. Now, example for this bagging algorithm is your random forest algorithm. Okay, what is random forest algorithm? Random forest algorithm is like, let us assume that a forest is having random trees. Okay, so here the main concept is it is used for classification and regression, and it uses multiple decision trees. You have learned about decision trees here. In the it was like you had multiple models and multiple learners. Now here it is decision tree. Random forest uses that model is nothing but decision tree. Okay, so these algorithms are widely popular because of robustness and it is easy to use because we are not using multiple models here. Instead, we are using the same model multiple times. So decision tree multiple times. Okay, so it is how. Let me show the diagram. multiple decision trees, right? The training data is bootstrapped. Each sample is sent to a decision tree. Decision tree, the gain, entropy, all that is calculated like the original, right? You are aware of decision tree, right? So it is going to take it as a tree model, right? It is going to take it as an input to the decision tree, and the output, whatever is given, is going to be majority vote averaging based on the type. If it is classification, it is going for voting, and if it is regression, it is going for averaging. Okay, so that is how normally a random forest algorithm works. Right. Now here, see, operates by creating multitude of the decision trees using training. Right. Each tree makes a prediction, and the final output is determined by majority voting or classification. For regression, the average. Random sampling with the replacement is done in variant. Here, it is not concerned about noise. It is not random forest will take noise. So you need not normalize, you need not standardize, or you need not work pre-process the data. It will handle the data however it is. And the high variance is converted due to the multiple usage of multiple decision trees. The high variance is converted into low variance. Okay. So each tree is trained on a different bootstrap sample. Each tree will be trained on a different bootstrap sample, and every decision tree is given a separate input. It can have a repetitive data value. Okay. Then this process helps to reduce variance. As I told you, high variance with multiple decision trees is converting it into low variance. And then each split in the decision tree and the random subset of the features is considered. Next. Now, as I told you, this averaging and voting. Now, how it works? As I told you, one people is giving you an answer and multiple people giving you an answer is really making the answer robust, the system robust, right? That same data set is being fed as samples to multiple decision trees. So normal single decision tree may not perform well every time. Yes or no? It will not perform well every time. So what I am doing here is, you are same training set, instead of this cross validation, you can pick up a random testing data set and you can apply it for testing the performance too, and you have multiple training sets given to multiple decision. So multiple models are working on the same data. Rigorously the training data is being trained. I understand. So that makes the system more effective and efficient. So this is the Python part or your implementation part. As I told you, scikit is for data science and machine learning. From scikit you have sklearn. Now the scikit library, it is called scikit library. You have been using it all these days. Yes. So there is nothing much here. What you have to do is the same decision tree, the same random forest, the same implementation like you are using for your other algorithms. But here you are using module called sklearn or ensemble. In ensemble, you have various classes. All classes, whatever I talked about so far, like your bagging, boosting, right, classifier, voting and aggregation, all classes are available in your module, in the library. Now it is imported, and it is, when you look at the terminology, it is like all are what we have been using all these days. Yes? So here, points to be noted are sklearn or ensemble, Adabus classifier, right? And then as I told you, here you see, we are using the Adabus classifier. Is that clear? Do you find any difference here? Okay. So this is about your value. Now, usually where are these random forests applied? As in, we have discussed about your dictionary applications. As in, you have applications for your various classification and regression techniques. You have for your random forest is also applied in the same areas, but where multiple evaluations are required, where appropriate decision making is required. Okay, so it is used in finance and banking, fraud detection, right? So far you have seen fraud detection for a single decision tree, But the same fraud detection here gives you the enhanced accuracy. Yes? Then you have credit card risk evaluation, same. You have same application, but a robust one. Then you have stock market prediction and option pricing, right? Then it is also used in natural language processing, sentiment analysis, and spam filtering, where you can discuss by spam filtering the accuracy of the systems to decide what to filter, how to filter your spam emails, and other technical and environmental fields it is used. Next comes your boosting. Bagging was similar. We talked the same for the ensemble methods for the bagging. It was a model. Now here, the same example we have seen, right, for both ensemble methods and bagging, where we have seen that random sampling, there was random sampling, bootstrap sampling, and aggregation. That was a different thing, right? Now what you are going to use is, you are going to use the output fed into another model. Now, here you have to understand the concept. In boosting, you have to understand the concept of base learner. Base learner. Okay? Now, there is also a difference. Here you are not going to use multiple models. You can use multiple models, and when you are using decision trees, decision tree for full depth will not be used. Okay, that we will see in the Adabus application. For now, to understand the overall concept of boosting, boosting will include the original data, just like your bagging, and it is given to different classifiers, different learners. The concept of ensemble learning. Now, when it is given to a classifier, it gives you an output which will have some properly classified and with some wrong classified things, right? This classified outputs. Whatever is correct is kept. This wrong data which is coming out of this, and it is yes several times, but it is here it is predicting as no. Right? So those wrongly classified data items are identified, and this set of data will be fed as an input to a new data, new classifier or new learner. You understand? I think actually when you are using the classifier, when you are getting the output, usually you use a base learner first. When you are giving the base learner, every input value will have same weight. Weights are same. Priorities, weights are priorities. Priority for every data value is same. But when it goes to the next level, here the weights are again rearranged based upon the performance value. Okay? So that is given by a formula. We will see in Adabus algorithm. Right? So now here you have ensemble classifier which are classified as strong learners and weak learners. How are you going to classify weak learners based on the weight cycle? Now here you have your boosting algorithm. Boosting algorithm is an ensemble technique that combines multiple weak learners to create a strong learner. How are the multiple weak learners? Individually it is weak. That weak is giving you a wrong output or misclassified output. That is fed as the input again to make it, and your filtering process is thorough here. Layers of filtering process. The data set is filtered, classified, then again reclassified, then again reclassified. You are using the weak learner multiple times and revising multiple times in order to make it a strong classifier. Right? So the weak models are trained in series and then each next model tries to correct the errors of the previous model. Now what you do usually is, first you have to initialize the model weights. Usually with an example, if I say there are suppose 8 data items, you can assign a weight of 1 by 8 to each data value. Okay? So in your data tuples, for example, if you in the tuples you have 8 data values, in your database you have 8 data values, number of values will be a 1 by 8, 1 by n will be a value. So you have to initialize a model weight. This initial value will be only for the base learners. Then you train a weak learner. Now this you give a initial input, that is initial weight to each value, and that is given to the base learner. Base learner can be any classifier. Here we usually use a decision tree again in the example, and then you have sequential learning, step by step, right? And then you have for every step you have a weight adjustment based upon the performance, right? So based upon the performance calculation, you are going to adjust weight of the output. You have two outputs, one positive and one negative, right? This output weights are readjusted and fed into input as your next step. Okay, Arabus algorithm. Here is an example. You have boosting algorithms, you have Arabus algorithm, you have gradient algorithm. Let us look at one algorithm, Arabus. Okay, Arabus algorithm, right? It is adaptive boosting, right? It is an ensemble method again. It combines multiple weak classifiers to create strong overall classifier. So multiple weak learners are classified as strong. Now here again it is developed in 1996. And the concept involves it iteratively trains the classifier focusing more on previous misclassified data points. So what is it concentrating on? The points which were not analyzed properly by person one, model one. Okay, that is the point you have to take it from the learner part here. Next, it assigns weight to each training samples, updating them for each iteration, and the final prediction is made through the weighted majority vote of all the classifiers. మీరు ఇన్పుట్స్ ఇచ్చిన తర్వాత ప్రతి దానికి అవుట్పుట్ వస్తుంది. ఎవ్రీ క్లాసిఫైర్ is giving you an output. Ensemble method is you have to train the classifier, and then you have to either use voting or you have to use averaging based upon classification and degradation, but both. So here also you are using the multiple classifiers. Again you are taking the outputs and using voting for classification and averaging for equation. Okay, so that is how it goes. Next, so weak classifiers in the Arabus perform slightly better than random guessing. Their simplicity allows Arabus to efficiently combine most classifiers. I am just looking for the diagram. Yeah. Okay, so no, let me just explain this in detail. So how it happens usually. So here also we are going to use the same decision tree, right? So what I am going to do here is, where in random forest you found the decision tree to have of any depth. We have seen the random forest algorithm. We have seen the decision tree like this. But in boosting, in Arabus algorithm, it will not use the entire decision tree. It is going to develop stumps. What is it called? Stump. Now what is a stump? Stump is a decision tree of only depth equal to 1. That means it will have the root node and the depth is equal to. Okay. So now what you are going to do is, first give your training data set to this stump. Now how are you going to decide? Now see, you have data set, multiple values, you have 8 values. Now how are you going to decide how to choose a stump and how to choose a base learner? Who should be your first learner? Right? Which decision tree should be your base learner? For that you have a procedure. For example, you know what is a feature? What is a feature? You know what is a feature? What is a feature? Okay. Okay, so now what you have to do is, what is a feature? Property, attribute. Yes? So you have data values 1, 2, 3, 4, 5, 6, 7 with 3 features to classify. Height, color, width, right? Length, whatever it is. You have 3 features to classify it. Okay. Now what you have to do is, you know what is gain and entropy, right? Right? You have to create decision trees for feature 1, feature 2, feature 3. Separate. For example, if there are 10 features, you have to create 10 decision trees. Compare the entropy of each decision tree. Yes? Compare the entropy of each decision tree, and then for F1 you have a decision tree, for F2 you have a decision tree, F3 you have a decision tree. Create stumps for all of the features you have in your algorithm. Then you have to miscalculate the entropy of every decision tree. Whichever entropy is low, that will be a base value. Whichever entropy is low comparative to all the values, all the decision trees or the learners, whatever you call it terminology, they entropy wherever it is low, that will become your base learner. Now that base learner is fed with the first set of training sample. Okay. Now whatever, when you are giving the input to the first set, here when you are giving the data into first set, that is whichever entropy is low. For example, we have F1 is low, so F1 will be your first model. So you will bootstrap your training data set and you will feed it into your first base learner, and here you get your classified output. What is your classified output? You have some 5 positives, 2 negatives, 2 misclassified. Right? You have 5 properly classified values and 2 misclassified values. Now these 2 misclassified values will be fed into the next one. Now when you are giving the data values here, the weight will be equal for all of them. Yes? Now when you once you got the misclassified values, what you have to do is you have to calculate the weight based on your misclassified values, which has a formula. Then that misclassified values, you have to calculate the performance. Performance is classified by 1 by 2 log e 1 minus total values, the total actual values. So for example we had 8, so 1 minus 8 by 1 by 8, right? Total actual weight, right? Total weights. 1 minus 1 by 8 is like 1 by 2 log e 1 minus 1 by 8 by 1 by 8. Whatever value you are getting here, that will be adjusted to the new weights. Are you understand? Now, previously you had initial value or initial weight as 1 by 8, right? Now, this answer will be your new weight. Right? So, now that will be adjusted into your new weight, and this will be fed into your next phase classifier. Right? So only weights, every data value is adjusted, having the adjusted weights. The adjusted weights and the new weights will be fed into the next more effective learner, that is your, say suppose it is F2, based upon the entropy again. Okay? And this is fed it as an output. Again here you will have a set of good classified and misclassified values. Again the weights and performance are calculated, and again the weights are adjusted and given to the third level. Right? Now you are going, here you have 3, right? So you have 3 rounds. It continues to how many features you have. And finally you are going to find out what the output is given or what by each of the classifier. Right? And then it is, if it is for classification, it is voting algorithm is applied, or if it is regression, averaging is applied. Right? Same again here. So if we look at the algorithm here, theoretically, see it is like that. First, what you are doing is, initially all training samples are assigned with equal weights. Okay, then the number of iterations or reclassifiers is set based upon the problem. Next, the algorithm begins by training first weak classifier on the weighted data. Right? You are giving the initial weights, and the first set is given by the weak classifier. How is the weak classifier decided? Based upon the entropy. Yes? Then you have, for each iteration, Adaptose evaluates weak classifier's performance. The error rate of the classifier is calculated based on the weighted samples. The classifier weight in the final ensemble is determined by its performance. As I told you, accuracy is performance. Performance measurable, you are going to define its weight, and then that is assigned to the sample weights are increased from misclassified instances that emphasize difficult examples. Correctly classified samples have their weights decreased every time. Correctly classified weights will decrease, wrong misclassified weights will keep increasing. Previously it was 1 by 8, now when you put it to the formula it is different. Right? Next, weights are normalized to sum to 1 before the training to next week classifier. Okay, the weight of each classifier is proportional to its accuracy. Better performing classifiers receive higher weights in the final model, and this ensures more accurate classifiers have greater difference. So every time you keep checking, the correctly classified weights keep increasing, right? So you have better performing classifiers receive higher weights. First entropy monarchy, you have lesser weights. Based upon its classifications, you have changed the weights and given it to the next level. Here weight was increased. Then in the next level again the weights will get increased and given as the inputs to the next level. So final weak classifier, that is the last classifier, will get the highest weighted inputs. Initially it was very low. By the end of the algorithm, it will get the highest weights. So that is how the final model, how we can predict. It combines all weak classifiers with their respective weights, and the predictions are made by a weighted majority vote across the classifiers. Again, voting and regularizing takes place. Where do you use boost? How it is using? Again, here also you have high variance, which is converted into low variance because of multiple usage of learners. You have multiple learners being used, right? So the high variance get converted to low variance. So boost is effective at reducing both bias. It is reducing both bias and variance. Okay. Then it is robust for overfitting, especially with proper parameter timing. Here, wherever you see, whichever model you take it a single one, the data training sample when you give, it overfits. When you use this concept only for a single decision tree, the training data get overfitting issues. Right? Now what happens here is the overfitting issues will be solved. Though there are remaining, but still majority of it is solved. Right? The algorithm is versatile and can be used with various base classifiers. Right? You can use multiple base classifiers. Next, limitations is it is sensitive to noisy data and outliers. Whereas in random forest I said it accepts noise. Here in AdaBoost, it is very sensitive. It is sensitive. It is sensitivity. It is like it is reacting to noise. So you have to adjust the noise. You have to standardize. You have to normalize your actual training sample. Then performance depends heavily on the choice of the weak classifiers. It is who you are going to decide what is a classifier. So you are going to decide who is a weak classifier and who is a strong classifier. So weak classifier, as I told you, based on the entropy, you have to calculate and identify. So you have to correctly choose a weak classifier. That is going to entirely depend, the performance is going to entirely depend upon choosing the weak classifier. It may require careful turning of parameters by number of iterations. Next, common applications of AdaBoost. Here again you find the applications of the entire ensemble methods, entire individual classifiers, right? You will find the same application, but where again as I told you needs decision making at the highest levels. You need robust decision making or correct, efficient decision making. Then in such situations you are going to use your AdaBoost. So it is majorly used in the areas of image recognition and face detection. Okay, and then you have text classification, spam detection. Text classification, spam detection were also there for your banning, but thoroughly used here in boosting. Okay, and then what are this algorithm is also used in bioinformatics and disease classification in medical, right? You have applications same for bagging, for decision trees, medical, yes, but here not all scenarios are the same as I told you, right? Combinational analysis is required, right? Thorough analysis, deep analysis is required. There it is start using your boosting algorithms. Right? The versions or the variants of your AdaBoost are your gradient boosting. Okay? So gradient boosting here is another algorithm. So gradient boosting and AdaBoost are different. Ensemble method but share same concepts. Concepts of ensemble is same, but the application level where you are applying the learners is different. Next, AdaBoost has variants like here AdaBoost has general AdaBoost also. The advanced levels of your boosting. Here, in the concept, it is like only introduction to bagging and boosting. So again, when you come to your application in programming in Python, same you can use it from the library scikit-learn, right? And then in the same library you have ensemble module, yes, where you are importing the classes, bagging classifier, boosting classifier, right? You can directly use AdaBoost classifier, right? You can directly use AdaBoost, and then you have anything else new here. Yeah. So you have a set of classes already defined in the library which are ready to use. So you can all you can do is you have to learn about the library, whether the scikit library, and in scikit library the names of the modules. Right? Here you can directly use bagging, boosting, right? And the name of the algorithm like the random forest, gradient boosting, and then you have your AdaBoost, right? Like this. Advantages of ensemble learning. Now, when it comes to the ensemble learning, overall advantages, when you find the methods, we have seen the same model being used multiple times. You practice something continuously, it becomes strong and robust. The same decision you are making several times using the same model, it gives you a perfect answer, better answer than the previous one. Yes or no? Likewise, when you consider ensemble methods, it reduces, the first problem is it reduces the overfitting. Okay, this overfitting issue has been seen in all the models so far. Wherever you see the model, like any model, name it, like your decision tree, any kind of decision tree again, right? Now, like the IDP or any other, then you have your other classification models, other regression models, any models will face the overfitting issue. That overfitting issue by using the multiple models here, multiple learners here, we are reducing. Then what was reduced? Variance was reduced. By using it multiple times, the variance which was very high in the other cases, that comes down. Okay, and then you have improved the generalization. The generalization is improved, and then the performance and the accuracy is increased. Yes or no? You agree or not? The same decision tree for the same input is being, see, like I come here to teach you something. I go out. You are the same set of students who have been applied to another algorithm, to the next teacher again. Right? What was missed here will be fed into the input, right? Will be given as a feedback to the next trainer, and the next trainer is going to first correct what is being wrong and then continue his process. So what happened is what was incorrectly done is being corrected. So all the mistakes are being corrected in the next classifier. So the accuracy is increasing or definitely it is increasing. Then robustness to noise, right? We are handling noise. When you see the consider the case of bagging, you need not handle noise there, right? You need not fill in the missing values there. It does on its own. So it can handle the noise on its own. What is noise? What is noise? All the inconsistencies, incompleteness, right? All these are corrected by itself, right? It is not going to consider, there is no need of you to do manually, right? Wherein you have to do for the other cases. First, pre-process the data, normalize the data, standardize the data, and then use it as an input, right? Here you are directly feeding the input, and directly you are bootstrap, sampling. Yes, sir. You are using your random bootstrap sampling, right? Then it is very flexible, right? You can use flexibility is is there though. You are using the same model, right? There is nothing new here. The same weak learners which you have identified are being you are making the same things more stronger, flexible to use, flexible to perform. Right? Next it is bias variance trade-off. There is a huge trade-off in bias and variance, as I told you. In all the cases of both your bagging and boosting, both bias and variance are being reduced. So there is a huge trade-off between the bias and your variance. Next, what are the disadvantages? Nothing is perfect. Again, see, when we learn the advancements, what you are learning now, machine learning, deep learning, right? There will be some more which have to be corrected. Like there are minor disadvantages where the ensemble are difficult to interpret the output of the ensembled model. Right? Now, what is the output? You cannot predict. All have to perform. Yes, right? So ensemble models can be more difficult to interpret here, it is difficult, and the output of the ensemble model is hard to predict and explain. Now, how you got the final output is the answer of several other outputs. Yes, so you are not going to explain a single output like it is the final answer. It is the answer of several other models. So it is like you are going to explaining the output or predicting the output will be a difficult task. It requires higher computation burden, especially for classifier training. Right? You have more computations every time you are. There is no one time use, right? There are multiple uses, multiple times, multiple steps. The same machinery. Earlier, what you did, you have divided into training data, testing data. One part of data was used for training. You have the output, and then you are using the testing data, and then you are checking the performance. If there is no difference, that means it is correct, and you have considered the output. But that now you are doing several number of times. Yes or no? So that is another computational burden. So you have a computational burden in your classified training. So bagging and boosting. Anything which is missed out or anything to be repeated can be asked for.